Hello, everybody, and welcome to chapter 12 in Dynamics. This is the actual first chapter of the book, but it's chapter number 12 because this is the continuation from the statics class. We cover a lot about when things are not moving, and now we're about to start talking about the study of particles and movements. Okay, and in order for us to do that, we're going to develop a few more chapters. Chapter number 12 particularly has been divided into two parts. So we're going to cover from 12.1 to 12.6, I believe, and then we're going to have a second video. So in order for us to talk about this, we need to remember this graph that we had in statics, right? Mechanics is a study of how bodies react to the forces acting on them. And we just spent a whole semester studying, the bodies in equilibrium, but now we're going to start developing dynamics. And dynamics is divided into kinematics and kinetics. In kinematics, we study or we're concerned about the geometry aspects of the motion, the path, the lift, and things like that. And then kinetics, which it's concerned with the forces causing the motion that we were studying in kinematics. So to do that, we're going to define continuous motion. And we need to define position, velocity, and acceleration, and how all three are, related to one another. All right, so at first we have a particle which travels along a straight line path defined by a coordinate axis S. The position of the particle at any instant relative to the origin is defined by the position vector r or the scalar s. Scalar s can be positive or negative, and the units for this particular one are usually meters or feet. The displacement of the particle is identified as the change in position, and the vector form for that displacement it's shown as r and then as a scalar form by s. The total distance traveled by the particle is a positive scalar that represents the total length of the path over which the particle travels. What is important here is that we understand exactly what is given by the book. So they told us that we have um, a path S and we have a particle right here, and this is the origin. So the distance from here to here, from the origin to where the particle it's located, P, we're gonna call that is S. And that S is a position coordinate. The distance from here to here, it's a magnitude, and that magnitude could be in meters or feet, right? That's what we said. And also, the direction will be given by the value, which could be positive or negative. All right. This particular one you know, has an importance because then when you have, and this is, let's say, at t equals 0, right? The beginning of the movement. But then you have the same path, but you have that particle p as it was given from here, right? And then a few seconds, you have the same particle at another location, and we're gonna call that P prime. All right, and this is the same as we're just talking about different times. The first one is at t equals 0, and then the second time is t equals, x, sometime after the beginning. Or for me, it's better if I call 1 and 2, you know. So we said that the distance from here to here was called s, right? So now we're going to call the distance from here to here S prime. The difference between them will be the actual delta S, and that delta S is what we call displacement, and that displacement, it's a vector quantity, and we have to make sure we don't get confused between that vector quantity and the distance traveled by the particle. Okay, we cannot be confused about that. You could have a positive displacement, or you can also have a negative displacement if the particle traveled from 1 right here to 2. So what I'm trying to tell you is that depends on the case, this value, the value of delta S could be positive or negative, and it will depend on each one of those cases. And don't forget that this is different from the distance it travels, and I will call that st, which is the total distance of the particle. And that is very important. Why is that? Because the next thing that we're going to define it's velocity, and velocity involves displacement and in vector quantity and also in a scalar quantity. But what is important about this is that the total distance is also taken into consideration to calculate one of the topics that we're developing. So velocity is a measure of the rate of change in the position of a particle. It is a vector quantity. It has both magnitude and direction. The magnitude of the velocity is called speed with units of meters per second and feet per second. So the magnitude is giving us a number and the direction is given by either positive or negative. That will change, right? So the average velocity of a particle during a time interval delta t can be obtained by using the following equation. An instantaneous velocity can be obtained also by deriving the position. If you time derivative the position, then you will get the velocity. The speed is the magnitude of the velocity, as I just said, but just remember that if you have, for example, the velocity in a scalar form, I'm sorry, in a vector form, and you want to get the magnitudes, it's just each one of its components, the square root of that. The average speed, it's the total distance that the particle travel over delta t, and that will depend on each of the particular cases. So, like I said, let's just recap a little bit. Velocity, it's equals to delta S over delta T, okay? That displacement that we have. If we want to get an instantaneous velocity, then we got to get the time derivative of the position. So that instantaneous velocity will be equals to Vs respect to the time. And the direction or the direction of this vector, particularly this is a vector, will be obtained by whether it's positive or negative. All right, if we want to get the magnitude of the velocity and that is giving us a vector, you know that the magnitude of that vector can be obtained by the square root of each one of bx to the square plus by to the square. That's how you can get the magnitude, and that will give you the speed. And then if you want to calculate an average speed, right, and let's call that an average speed, that will be equals to the total distance traveled over an interval delta t. All right, if you have enough information, then you will be able to calculate both of them. Acceleration. Acceleration is the rate of change in the velocity of a particle. Remember, the velocity was the rate of change in the position, so now acceleration is the rate of change of the velocity. It is a vector quantity, and the units for acceleration will be meters per second square or feet per second square. I'm pretty sure you covered this in statics and also, physics 1 and 2. The instantaneous acceleration can be obtained by deriving the velocity. So you can get instantaneous acceleration by deriving velocity respect to the time, or you can double derive the position instead of the time, respect to the time, and it'll be the exact same thing. So what is important for us to know is that the acceleration is very connected to velocity, as I just said. Right? So if we want to get the average acceleration, we have to remember that that will be delta v over delta t, or the change in the velocity in an interval time. If we want to get an instantaneous acceleration, then let's call that instantaneous acceleration. That will be equals to the derivative of the velocity respect to the time. And this could be positive or negative, depends on your sign convention. And we're going to get into that, but it's very similar to what we did in statics. All right. And then also you can know that if that's true and the derivative, in order to get the velocity, you have to derive the position. You can also say that the instantaneous acceleration will be equals to the double derivative of the position respect to the time. What is important here is that you realize that you can actually combine both equations, like from acceleration and velocity in order to get a third equation which will depend on both of them. And how so? Well, you know that velocity it's equals to ds, the derivative of the position respect to the time, and then acceleration it's equals to the derivative of the velocity respect to the time. If I solve dt for both of them, for example, this one would be dt will be equals to ds over velocity, and right here will be dt equals to the derivative of velocity over acceleration. If I go and say dt equals dt, then I'm going to get a new relationship, which is ds over v and dv over a. And if I want to develop these further, then I will get a ds it's equals to v dv. And this equation, guys, it's given in the book as the result of combining the two equations that I gave you, the one that defines the velocity and the ones that define the acceleration. With this equation, you can solve for unknowns when the case is given. And finally, as a recap of what we just said, so we just have to know this, right? So if you differentiate position, you get velocity, and if you differentiate velocity, you get acceleration, right? That's what we just covered. But on the opposite side, you know, what oppose differentiation, it's integration, right? So if you do the opposite and you integrate acceleration, then you will get velocity. And if you integrate velocity, you will get position. That's what's really important here, that based on these three equations given, the ones that we just developed, you are able to get anything, and just remember that all of these equations were developed in a time interval, okay? From t equals 0 to t equals, whatever time it is, then that will depend on the case. If I were you, I would save these relationships or these relations, so you can use them on the exam. That's exactly what it's needed, when solving exercises with this. So, all right, keep in mind that you have two, three equations. So the first one is the one that involves velocity, ds over dt. Then the one that involves acceleration, which is dv dt. And then as the result of relating 1 and 2, we get a ds equals v dv. What it's very important for you to know is that you are not going to be using the three equations at the same time. It's always two out of the three, either this with this, or this with this, or this with this, okay? That's exactly how it works. The way I see it, and this is something that I developed myself when I was studying engineering, right? You have position, velocity, and acceleration. And you always have to calculate something based on what you're giving. If you're given the position, then you need to get velocity and you need to move in that direction, or sometimes you need to move into that direction. From having the acceleration, you need to calculate velocity, or from having velocity, you need to calculate position. If you're moving into that direction from left to the right, you're going to differentiate whatever you have respect to the time, whether it's position or velocity. And then if you're coming from here to here, then you're going to do the opposite, which is integration. All right, save this and you will not have any trouble. If you memorize that now, believe me, you will have what it takes in order to get what's coming. So now there is another case. The three kinematic equations can be integrated for a special case when acceleration is constant. A common example of constant acceleration is gravity. When you have a body that is falling, that is freely falling, right? The only thing, neglecting obviously the air resistance, will be the gravity, and that's the only acceleration that the body will get. acceleration due to gravity, and that is going downward. And the three equations can be converted into this because then the acceleration will be outside of the integral, leaving you with this. And obviously, don't forget that you're going from the initial velocity to the final velocity from t equals 0 to a t interval. And then when it comes to position, it's from initial position to a final position. The same thing for the time interval. And as you develop the equations, then you're going to get three new equations. And these are only when acceleration, it's a constant acceleration. Okay, when that information is given, that's when you're going to use those equations. Otherwise, you can't. All right. As I told you at the beginning of the semester, I will try to include a few examples so you can kind of get used to the data and everything that is given for exercises. So let's do this one very quickly. A particle travels along a straight line to the right with a velocity of, or a velocity that it's placed in terms of t as an equation, where t is in seconds, also as the position equals 0 when t is equal 0. They're giving you like initial conditions. We need to find position and acceleration when the particle is at t equals 4. What is important here is that we understand what it's given so we can actually plan for what's coming. So the data we have, it's an equation of velocity equals to 4t minus 3t squared. That's meters per second. And we're also giving initial conditions. When the position is 0, t is equals to 0. And we need to calculate the position and acceleration when t is equal 4 and acceleration when t is equal 4. All right. If that's the case, for me, it's very clear. I was given with an equation, and therefore I can use the equations that I will have to integrate and differentiate in order to get what I need. So I know that acceleration it's equals to the derivative, the time derivative of the velocity. So very simple and straightforward. So it will be the derivative or of 4t minus 3t squared respect to the time, and that will give me 4 minus ct. And then because they're asking me, so when t is equals to 4 seconds, I can say that my acceleration it's equals to negative 20 meters per second square, or you could say acceleration is equals to 20 meters per second square going to the opposite direction of the positive. Okay, either one of them will work. So now we need to calculate the position. How do we get that? So we were given with an equation for velocity. So we know that velocity is equals to the differentiation of the position respect to the time. If I go ds will be equals to v dt. If I integrate on both sides, right, and this is coming from 0 to s, which is the position, and this is from 0 to 4. So I will get that s is equals to the integrate of 4t minus 3t squared dt, and this is from 0 to 4. And as I solve this integral, I will get 2t squared minus t cubed, and that is evaluated between 0 and 4. As I plug these values, I will get that s it's equals to minus 32 meters. Okay, or you could say 32, sorry, 32 going into that direction. And don't forget, sorry, let me just go like this, 32 meters going into that direction. Either one of them will be cool. Okay? Very simple, guys. What is important here is to realize that when something is given, you can utilize the equations to your advantage so you can get what you need. All right, so I plan on giving you a second exercise, a little bit harder, right? So a sandbag is dropped from a balloon ascending vertically at a constant speed of 6 meters per second, okay? The bag is released with the same upward velocity of 6 meters per second at t equals 0 seconds, and it hits the ground at t equals 8 seconds. So we need to find the speed of the bag as it hits the ground and the altitude of the balloon at this instant. Okay, so what we need to know about this is the sandbag as it will develop a free falling movement. It is experiencing a downward acceleration of 9.81 due to gravity. So we can just now by default that is a constant acceleration, and therefore I can use the equations that I solved towards the end, of my explanation. So how do we do this? And again, I can just make sure I get the right data. I was given the speed equals to 6 meters per second, and they said that is constant, right? The delta t, it's coming from 0 to 8 seconds, and acceleration is constant to minus 9.81 meters per second square. And what I have, right, if this is the ground, I'm a terrible drawer. Right here, the back, it's getting off the balloon, and then at some other point, I will have the balloon, and the back will be right here on the ground. Okay. What is very important that to know is that when the back was released from the balloon, then the balloon kept going up as the bag was going down. And that's something that is important for us to remember. Okay, so when looking at the bag, what we need to know is that we can use the equations that were given at the end of the explanation. You remember that the velocity can be obtained at any point by using this equation. Final velocity is equals to initial velocity plus acceleration time, right? AT. That's when the acceleration was constant. And then in this particular one, if we study the back, we know the initial velocity because it was constant at 6 meters per second. We need to get the final velocity. So this is pretty easy. So if I plug into the values, I get that the initial velocity is 6 meters per second plus minus 9.81 from the acceleration, and the time is 8 seconds, right? Which is what they're asking us. So BF will be equals to minus 72.5 meters per second. And I always keep the sign, I don't use the arrows or anything like that. So now I know the velocity of the bag, at the end, at 8 seconds, right before it hit the ground or. And now I need to calculate the position of the bag. What is very important here is that I establish my zero. So for me, this would be the zero because the zero was released right here. When it was released, the bag for me, that was S. At t equals 0, my position was 0. And then now I need to calculate where the bag is going to be located to see how far the bag was from the ground floor. Okay, so for that, I will use position at t equals 8. It's equals to initial position plus initial velocity. Okay, that's equation I need. Knowing that this guy is 0, BO is 6 because it's constant, then the T it's 8, I have the acceleration, which is minus 9.81, and t again, it's 8 seconds. If I plug into all the values, I will get that the position of that bag, it's equals to negative 265.9 meters. And that will be the distance that the bag travel. What is important here from this exercise is that you have a clear plan of what needs to be done. When I'm looking at the whole thing, right, I think the projections or the drawings I had is what will make things clear or not clear. All right. If I just focus on the back, putting this as my zero, that's why I'm getting a negative displacement or a negative position, right? So the back traveled from here to the ground, from here to the ground, to 65.9 meters. But they're asking me also the altitude of the balloon by the time it hit the ground. As I told you at the beginning, when the back was released, these kept going up and the back was going down. Important for us is to realize how can we calculate the total altitude, because that's what they're asking, right? So as the back was released, the balloon kept going up and the back was going down. Right when it hit the ground, the distance traveled of the back, because that's what I calculated, how far the back went from the balloon to the ground floor, was equal to 265.9. And it was negative because obviously that's my zero, so it went down that path. So now I need to calculate how far the balloon went when t was equals to 8 seconds. So if that's the case, for me, I just need to understand how I should use the equations, okay? And that's the important thing, because if you know how to use the equations, then it'll be very easy for you. So I would say that I'm looking for the position of the balloon when t was equals to 8. That's what I'm looking for. That would be equals to the initial position of the balloon plus the initial velocity of the balloon times t plus 1 over 2 acceleration time to the square. And remember, we're talking about the balloon. So the position of the balloon at t equals 0 was 0 because that's what the balloon went. This is 1 and this is 2. At 1, it was 0. The velocity of the balloon, it's given because it's the same 6 meters per second that was given. This t, it's equals to 8 seconds. And right here, I want you to understand that the only one experiencing a downward acceleration was the back, not the balloon. And therefore, this whole component is 0. That will give you a very simple equation to solve as S of the balloon, it's equals to B O of the balloon times the time. All right, in this case is 6 times 8 seconds, and that will give you a total of 48 meters. So as the bag was traveling to 68.9 from here to here, the balloon traveled in 8 seconds, 48 meters. So therefore, the altitude of the whole thing, or the distance traveled by the balloon in the back, is going to be from here to here, and that is the 48 plus the 265.9, and that will give you a total of altitude will be equals to 48 times, I'm sorry, plus 265.9, and that will give me a total of 313.9 meters as the altitude. And with that, I got, the solution they were asking me to get. All right, so now we're going to talk about something that is called erratic motion. Erratic motion, it's pretty much very simple and easy. I just show you how to get position, velocity, and acceleration by using the equations. But sometimes these movements are going to be described by graph. And the important thing is that you understand that you can also get this value from a graph because the equations is just a graphical representation. If you plug values into those two variables, you can get a graph, right? That's from math, simple math. The approach builds on the fact that the slope and differentiation are linked, and the integration can be finally found as easily finding the area under the curve. And that's the definition of an integral, right? The definition um, of a differentiation is just the slope, and the integration, it's the area under the curve. It's very, and it's simple as that. So for the SD graph, right? If you have an SD graph given and you calculate the slope of that graph, that will give you certain values, right? As you calculate the slope at each one of the intervals. If you take those values and you plug them into a VT graph, then you will be able to find the graph of the velocity. And if you go with the VT graph, it's exactly the same thing. So you have a VT graph, right? And if you get the slope of each one of those points at t equals 1, 2, and 3, you will be able to find the acceleration graph. Okay, something as simple as the acceleration, it's equals to the time derivative of the velocity. So if you calculate the slope of each one of those points, you will be able to find your acceleration graph. And AT is exactly the same thing. So now we're going backwards, right? So if you have your acceleration time, your graph, and you get the area under the curve, or you integrate that velocity, you will be able to find the first point. And if you keep doing that, as you keep adding the points, you will be able to construct your VT, okay? And you can do the same thing. Just do you remember when I told you that position, velocity, and acceleration, they were very, very connected? So if you're moving from here to here, and if you're moving from here to here, for this one you had to differentiate respect to the time, and for this one you have to integrate. So now we're going to add slope when it's graph and area under the curve, right? If you memorize this, guys, you will not have any troubles at all. The whole thing with this erratic motion is that we understand that acceleration, position, and velocity, they are connected, first of all. And second of all, that you can get these values by integrating or differentiating. But you can also get it by calculating the slope and the area under the curve when graphs are given. And as I promised, we're going to do an example so we can understand how to calculate this and how to deal with graph. You're going to have one of these on the exam. All right, so given the VT graph for this car moving along a straight road, you need to find the acceleration time and the position time graph over the interval shown. And you were given with this graph. So what do we do? All right, so we need to understand that we have intervals here. So we have from 0 to 5 and from 5 to 15. If we break up this into this part by utilizing the equations given, shouldn't be any problem. So how so? So for example, if we're going to get, and remember, S, V, and T, I'm sorry, and A, acceleration. We were given with velocity, and we're now going to do the AT graph. So we're going from here to here, which means we're going to differentiate respect to the time. How do we do that? So very easy. So acceleration, it's equals to dv over dt, and v was given from 0 to 5. That will be the time derivative of 30t over dt, and that gives me a plain value of 30, right? And then right here, I will do the same thing, dv dt, and this is equals to the time derivative of minus 15t plus 225. And that gives me a value of minus 15. If I want to construct the graph, it's just simple values, which means it's going to be a plain line. So we'll go like this. So the first, and this is a t, and right here I have 5, and right here I have 15. So the first number is 30. So that's my 30, and it's just a number. It doesn't have a slope. It's constant throughout. Okay, so that's my value. And the other one is minus 15, which is here from 5 to 15. That's it. That's my graph. Okay, remember that when you differentiate a line that has some inclination, you will get a line, okay, because it's constant. And if you integrate that, on the other hand, you will get a curve, right? And that's where we're going right now. The AT graph is given, like I said. I just showed it to you. Well, I did it. This is more beautiful, obviously. So now, if we're going to get the VT, right? And I'm going to take you back to this position, velocity, and acceleration. And we're going into this direction, okay? Because we were given BT. So now we need to build ST. Therefore, we're going to use the integral. And you have two options here. You can either integrate, or you can also get the area under the curve for these values. Okay, both of them will work. But in my case, I'm going to go ahead and use the integration. I think it will be much better. All right. So from 0 to 5, I know that v it's equals to ds over dt. If I solve for ds, this is equals to v dt. I will integrate on both sides. These go from 0 to the square. That has to be evaluated between 0 and 5, and that gives me a value of 375 meters. Okay, when it comes to this is from 5 to 15 seconds, then now I need to go with the same equation. V is equals to ds over dt. ds is equals to v dt, and now I'm going to integrate from 5 to 15, but here I'm going to go from the s that I calculated, which is 375, to s, because I don't know exactly what I'm going to get. So s minus 375 would be equals to the integral of minus 15t plus 225 dt. S minus 375 will be equals to minus 15, that multiplies to 1.5 t to the square plus 225t, and this has to be evaluated between 5 and 15. My total S would be equals to 1125 m. And with that, I can build, you know, the following graph. Right here, 375, 125, and it goes like this. All right. Some remarks from this, guys, is that you can easily work with either the slope, of a line. That's pretty much a mathematical equation, or you can get the area under the curve, or you can use integration and time derivative. And at the end of the day, it's going to be totally up to you. I'm not going to ask you which one you should use, but just use these examples I'm giving you to kind of get your own way. And we're going to briefly cover about curvilinear motion. All right? To be perfectly honest with you, I want you to go over this. I will not put this in the exam. All right? A particle moving along a curved path undergoes curvilinear motion. Since the motion is often three-dimensional, vectors are usually used to describe this motion. A particle moves along a curve defined by a path function S. The position of the particle at any time is designated by a vector R, which obviously it is, dependent of the time. The magnitude and the direction of R will vary with time. If the particle moves a distance along the curve during time interval delta t, the displacement is determined by the vector subtraction. So if you have this, you know, position that you have your R, and then if you move from that to here, which is pretty much the picture you have right there, that will give you an R prime, and the vector, the resultant vector will be given by subtracting R prime minus R. And this is very similar to what we had in statics, because when we were covering how the vectors were reacting in terms of position, that's exactly what we did. Velocity, it's the same definition, but the important thing with this is that when we're talking about curvilinear motion, we have to do it in terms of vectors because it's easier for us to define the components and then work them out as vectors. It will give us both the direction and the magnitude, and with that we can define that much better. So the velocity represents the rate of change in the position of a particle, the exact same definition that we had. The average velocity is calculated with the same formula, instantaneous velocity, same formula as the time derivative of the position, and the velocity vector is always tangent to the path of motion. That's the only thing that is new to us. Okay, when you have curvilinear motion, the velocity vector is always tangent to the path of motion. We're going to talk more about this once we start working with these velocity components and acceleration components. Okay, as you know, the magnitude of V is called speed. Since the arc length delta S approaches the magnitude of delta R as t is equals to 0, the speed can be obtained by differentiating the path function, which it's, dependent of time and displacement, okay? Note as before that the speed is not a vector, it's a value, all right? And now we go with the acceleration. It's exactly the same thing, okay? It represents the rate of change in velocity of a particle. It is exactly the same thing. The only difference now is that it's not a straight motion, it's now curvilinear motion. If the particle velocity change from v to v prime over a time delta t, the average acceleration during that time, it's calculated as delta v over delta t, and delta v is calculated as the subtraction of the two vectors, just as we did it with the position. Okay, the instantaneous acceleration is the time derivative of the velocity or the double time derivative of the position. So as you start looking at the path of this velocity, all these velocity points will form a new path, and that path is called the autograph. Okay, and that's very important. If you put all of the points of this velocity, the arrowhead, as you combine all of these points, then you will start developing another curvature, which is called the autograph. Okay. So the acceleration, okay, is tangent to the autograph, but not in general tangent to the path function. So keep that in mind. And as I said, I was going to cover that very briefly because we're going to develop that even more, on the next chapter. Now we're going to talk about rectangular components. This is when things make more sense, if I'm honest with you. If we treat everything, when things are given in terms of vectors and we treat them as components, it gets a lot easier because then you can put together I with i's and then j with j's and k with k's. And as you have each one of the coordinate system, then you will be able to calculate those and you will be able to calculate everything that you need. Okay. It is often convenient to describe the motion of a particle in terms of x, y, and z, or rectangular components, as we said. The position of a particle can be defined as an instant vector given by its components. You know, if you have a particle located here, you can define that from the origin as you give values to x, y, and z. So the magnitude of those vectors is the square root of its components. This is pretty simple math. And then the direction will be defined as the unit vector. And we cover that in the statics, okay? So don't worry about that. You will, once you have the location of the vector and you use one of the unit vectors in order to localize your position, then you will be able to define that. With the velocity, it's the exact same thing. You have to remember that the velocity will have, and if you use the time derivative of the position in x, then you will get the component of the velocity in x. If you do the same thing for y, then you will get it in y, and if you do the same thing for z, you will get the same thing for z. Then once you have all of the components, you can get the magnitude of the velocity just by getting the square root of each one of those components to the square. If you sum all of them, then you get the magnitude and the direction of B, as it was stated before, is tangent to the path of motion. Okay? When it goes to the acceleration, it's exact same thing. By using the equation that was given at the beginning of the chapter, which is acceleration is equals to the time derivative of the velocity or the double time derivative of the position, that you can get the components, because this is from the assumption that you will always be given the components of velocity or will always be given the components of the position. If you use the time derivative of the component in x, you will be able to get the acceleration component in x, and the same thing for y, the same thing for z. Okay, the magnitude of that vector is as all of the magnitude, square root of each one of its components, all of them combined. The direction of acceleration is usually not tangent to the path of the particle, okay? And we're gonna talk more about that because as you remember from statics, we were also developing normal acceleration and things like that. That is coming too. Okay, and now we're going to talk about the last thing of this video, which is the motion of a projectile. Guys, this is quite important. All right. Everything that we've been developing is like kind of clicking, and I will show you with equations what it means. All right. Projectile motion can be treated as two rectilinear motions, one on the horizontal direction experiencing zero acceleration, and the other one in the vertical direction experiencing constant acceleration or due to gravity. Okay. For illustration, consider the two balls on the left. The red ball falls from the rest, whereas the yellow, the yellow ball is giving a horizontal velocity. Each picture in this sequence is taken after the same time interval. Notice that both balls are subjected to the same downward acceleration since they remain at the same elevation at any instant. Also note that the horizontal distance between the successive pictures photos of the yellow ball is constant since the velocity in the horizontal direction it's constant. So this is like the distance from here to here, from here to here, from here to here, from here to here, and so on and so forth. As it moves, right? Since it's the same component in the x direction, it moves constantly. All right. And that's what we're doing right now. We need to study the kinematics equations for a projectile motion. So when you have a projectile, you have a ball right here at t equals 0 that is kicked or it is thrown with a projectile movement and goes from here to here. As it goes, if we are neglecting um, the air resistance, we can say that the only thing that this ball is experiencing will be a downward acceleration of the gravity, okay? So, and it's constant, so we can say that that acceleration is, minus the gravity, 9.81. What I'm trying to tell you is that when working with projectile, it is much better to divide everything into horizontal motion and vertical motion. And why is that? Because horizontally, you have to deal with less things since there's nothing, acting on the horizontal direction. Whereas on the vertical direction, you have the gravity, and therefore the equations are going to be a little different. So, note that the only acceleration, like I said, is going into the y direction, and since the x direction does not have an acceleration, then the equations that we were solving before are going to be simplified to this. So in horizontal motion, we have three equations, right? B at the end, it's equals to initial velocity times acceleration, I'm sorry, plus constant acceleration time. And remember, this is horizontal movement, okay? And then we also have another equation, which is position at the end. It's equals to initial position plus BOT plus 1 over half gravity times square. What happened? What do we have in horizontal movement? There is no acceleration because we're neglecting the air. So therefore, this guy is 0. This guy is 0 as well. Okay, so the first equation tell us, and this is BOX, position in the x direction for all of this. So then the final velocity, it's equals, is exactly the same one in the x direction. Okay, we get the first equation, and that's what it's given right here. Then for the other one, we're going to substitute s, which is position for x, because we're talking about the x. Position at the end, it's equals to position at the beginning plus the velocity at the beginning x times, and that's the second equation. So, which is this. So when we are dealing with x components, it's a lot easier because we don't have anything else affecting the particle. Okay, the particle would be affected, yes, by just the gravity in the y direction, and therefore the equations in the y direction will be a little harder than they are in the x direction. So when talking about projectile motion, these two equations in the x direction is what you need. And now for the y direction, the acceleration will be given as minus g, and the application of the constant equations will yield to these ones. How did I get to this point? Well, it's the same equation. So final velocity is equals to the initial velocity times acceleration constant t. Since acceleration is minus g, that's why you have this equation. For this one, it's position at the end. It's equals to position at the beginning. And all of this in the y direction, plus the velocity on the y direction times t, plus a t squared divided by 2. Since acceleration is negative, that's why you get this. And then they just substituted the position with the y, and that's how you get this equation. And this one, it's the third one, which is given from bf to the square, it's equals to bo to the square, plus 2a that multiplies s minus so. It's the exact same one. And do you remember why we're only going to use two equations? So you remember that when we developed this at the beginning, I told you that you're only going to use two out of the three because the third equation is the result of using the equation that established velocity and acceleration. Okay, when we combine them both, that's when we got the third equation. So that's you are given with VA, and they're also giving you the angle on which VA it's given. We need to find the horizontal distance it travels, like the distance between this and C, you know, x at the end. And then we also need to calculate the velocity when it hit the ground. All right? Sounds like a plan. So when that happens, right, the first thing that needs to come to your mind is the equations, right? So they're asking me for the position at C, and that it's equals to the initial position plus the component of the initial velocity times t. This is what I'm looking for. This is given, which is 0. That's initial position, assuming that this is my origin. The velocity, it's given right here as the x component of BA, which is the cosine. This guy right here, it's forming a triangle. All right, so the x component will be equals to 10 cosine 30. So now, right, I realize that I don't know t and I don't know xc, so I can solve this. So what about if I try with the y direction? The y direction, right, at c, it's equals to the initial, or let's call at a, plus the y component of the velocity times the time plus 1.5 acceleration t squared, right? That's all I need. And since the only thing I have it's the acceleration going downward because that's what they told me. Sorry about that. I know that the acceleration is constant and it's equals to minus 9.81. I have everything because in the y direction this is 0, this is also 0, right? The y component of the position at A is 0, the same thing for z. BOY it's given, it's right here. And I only have to solve this quadratic equation, right? Let's plug into the values. 10 sine of 30 that multiplies t, right? Minus 9.81 that multiplies t to the square divided by 2. This is equals to 0. If I solve this quadratic equation, I will get two values of t. The first one will be t equals 0, and the second one is t equals 1.019. And this is very expected. Why is that? Because you were using the following equation. Remember, y at A, it's equals to y at Z plus BOYT plus 1.5 acceleration time to the square. You're using an equation that has the locations of A and C. So your first t is t equals 0, and your second t is t equals 1.019. With that time, the time has been developed. You can plug this value into the equation that we had at the beginning in order to get it. So how so? xc, that's equals to xa plus box, then multiplies times. So this guy is 0, right? Because it's the beginning. xc will be equals to 10 cosine of 30 that multiplies what I just calculated, which is the time, and this is giving me a total of 8.83 meters. Okay. Now what is important for me now is to get the components of Vy and BCy and BCx in order to calculate BC. So I know that BC has two components, BCx and BCy. And then if I want to get the magnitude of this vector, then I need to calculate the square root of these components. Okay, that's very simple. So I know that in projectile movement, the velocities, the components are the same. So B, Cx is the same one as VAX. Remember, in projectile motion, the components in the x direction they are the same because there's no acceleration involved in that, right? Did you remember that? Then when it comes to the y direction, then we got to use this equation. Okay, just plugging back and forth. So VCX, it's something as simple as 10 cosine of 30, which is equals to 8.66 meters per second. When it comes to VCY, this would be equals to 10 sine of 30, which is VAY, minus gravity, which is 9.81, and the time, which is 1.019. And this is giving me a total of minus 5 meters per second. And it makes sense because it's going downward. So now BC will be equals to the square root of 8.66 to the square plus minus 5 to the square. And as I get that value, will be a total of 10 meters per second. Simple as that, guys. It's very straightforward. It's just knowing what equations to use and when. That's all we need to know. All right, guys. With that, I conclude the video. I hope that it has helped you, that it has helped you a lot. What matters here is that you go read the book, understand what it's covered, all the way to 12.6 so we can get ready for what's coming next week. All right, that's it for today. Let me know if you have any questions. Shoot me an email or get in touch with me. Thank you very much for watching.